Hello and welcome to my final project presentation. My name is Michael Brand, and today we are going to be talking about peer-to-peer processor sharing. Now, what is that? So, hang on a second. Here we go. All right. So, we all know that there are server farms that exist that are able to take in incoming requests and distribute those requests for processes amongst themselves in order to accomplish load balancing. And this allows them to ensure that no server is ever just sitting idle while one or many of the others are working their tails off, exhausting all of their CPU utilization. But the thing is, networks come in all shapes and sizes, whether it's a large server farm or a small LAN party, or maybe it's just the Citadel's network or a computer network at some library. And there's really no reason that I can think of why we couldn't use this exact same principle of load balancing in a much smaller setting. So we're going to see if there's a possibility that we can do something like that on a smaller, potentially more decentralized network. Now, resource sharing in peer-to-peer networks is something that's been around for a long, long time. It's been around since the days of Napster. And that would allow computers to share one another's resources, but usually those kind of resources would be in terms of files or memory storage. This implementation would aim specifically at sharing processor power instead of memory, and that should alleviate the load that any one processor might feel that is temporarily at perhaps the limits of its abilities and CPU utilization. That should theoretically be actually much easier to achieve than peer-to-peer file sharing, given that files are something that's going to persist in memory, and the need for CPU power is something that shifts with the wind. Maybe 1 second one processor is in need of as much CPU power as it can get, and the next minute somebody else is the one that's really in dire need. Now, process distribution is something that we just talked about moments ago. Usually it's done with server farms and depends upon, as we see here, a load balancer. The load balancer receives requests that come in, it assesses its pool of servers, and it distributes the incoming request to whichever server it decides is best suited for the task. Now, our implementation is going to take this exact same concept, it's going to bring it down and try to put that on a much smaller scale network. It's also going to see, we're also going to try to decentralize that process, so we're not dependent upon a load balancer at all. Now, with this kind of an implementation, there is just way too much to cover in any one single project. There's a little bit of networking going on, there's a little bit of processor sharing going on, there's a little bit of security that would definitely need to be taken into consideration. So for our purposes today, we're just going to be focusing specifically on the processor sharing policies and the load balancing policies in order to determine what we think would be optimal for such an arrangement. Later work, we can then focus on the aspects of implementation, including network topology, security, and other concerns. Now, let's talk about related work. So, let's talk about load balancing. There are a whole bunch of different policies in terms of load balancing that needed to be considered. I've just listed a few here that I thought were particularly interesting and useful for the examples and the illustrations that we've drawn out so far. So the first one that we have here is the round-robin load balancing policy. All this does is it distributes jobs one at a time to each machine in sequence. This is great for large server farms because when you've got the load balancer that we talked about earlier, load balancer, all this thing would have to do is just keep track of how many servers you've got and make sure it knows which server it just gave a job to, and it can just go in sequence. 1, 2, 3, 4, 1, 2, 3, 4. Doesn't have to keep track of the state or the burdening, how highly burdened each of these servers are. It just needs to know where it is in its sequence. Now the join shortest queue, though, is one that is much more efficient as far as distributing load. It's actually going to assess each machine, and then it's going to issue the process request to the one that has the shortest queue. This is really great, but it is only really functional for smaller scale networks. Once you got on the order of 100,000 servers that you're working with, that's the point at which it's just too taxing to keep track of all of that, and so it's no longer efficient. So joint shortest queue is one that only works for smaller networks. Now the shortest queue out of D policy, on the other hand, is one that's going to take some number D. It's going to choose that many randomly chosen machines, and it's going to assess only those machines rather than taking a census of the entire server farm, and it's going to issue the process request to one of those machines specifically that happens to have the shortest queue. Now, even if we're only selecting two random machines out of our entire group, that's still going to get almost optimal efficiency, and it's doing only that is going to be a lot more scalable than working with the join shortest queue, which of course is, as we've said, not going to be optimal after you reach a certain number of servers. Now, in terms of processor sharing, there are a whole bunch of different processor sharing policies. Now, processor sharing is something that exists strictly within a single machine. Processor sharing is something that came into existence back in the ye olden days when we had time sharing when there were 10, 20 or so users trying to access the exact same machine, and everybody had to take their turn in sequence. It is, however, still something that exists even today, though to a much lesser extent. Now, oftentimes, with processor sharing, you have many different classes of processes that each exist on their own separate queue. Now, with GPS, which stands for Generalized Processor Sharing, each queue is given its own weight, and that is going to determine the probability of it being chosen relative to its peers for the next time slot on the processor. It's going to be using, as we can see in this diagram here, we've got each of our different weights, 1, 2, 3, and it's going to select from among these three queues depending upon how it handles that. It's going to make a random selection depending upon these weights. And it's going to use a single selection for that service. It's very efficient to do it this way because you're only making one single calculation. Here we've got the hierarchical GPS, which is going to make a determination based upon preset probabilities if the first class is going to be chosen before considering any of the others, and the second and third sequentially. So first it would make this choice R up here, and it would decide, okay, with 20% probability I'm going to D. There's an 80% probability that I'm not going to D, in which case I would go to either A or B depending upon these probabilities here. Now, if there is no A, that's not going to affect how likely we are to choose D. We're still going to choose D with only 20% probability overall, but then if we get rid of A, if A doesn't have any processes in it, that's going to mean that C is going to take all of these probability. There's an 80% probability then that we're going to end up choosing B. Whereas with something with the generalized processor sharing, if one of these queues is empty, then the other two will inherit its probabilities proportional to their own. Now, for the hypothesis and implementation of this project, what we're going to do, our hypothesis is that a network of machines capable of sharing processes while under duress will produce lower sojourn time and higher throughput than one which cannot. So we're going to have many instances that are going to be created on Amazon Web Services EC2 to form a mesh network. The machines will be arranged into a chord-structured, decentralized ad hoc network, and each machine is going to perform the shortest queue of D survey of machines in its own distributed hash table. The distributed hash table is something that is going to be present in a chord network, chord-based topology. It's going to select one from that it has the smallest queue from among only those servers that are present in its distributed hash table. Each machine will then use the hierarchical GPS queuing policy as well as FIFO to organize processes within each queue. I forgot to mention earlier, So these policies only decide which queue we're pulling from, which queue is presently going to be next to get onto the processor. But within each queue, it also has to have its own processing, different policies such as FIFO or shortest task first or some other kind of prioritization. Alright, all nodes will randomly generate some kind of an expensive task with the probability model. Probability of generating that task is going to be modeled upon the Markov modulated Poisson processes. Well, when CPU utilization is going to exceed 90%, then that is when a processor is going to begin issuing unserved processes to its neighboring machines. What variables we're going to be controlling here, just for the sake of standardizing across all of our different machines, we're going to make sure that the tasks are going to be generated with the probability with which it's generated is going to be standardized, and it's going to be based upon the Markov modulated Poisson processes. Every processor on the network is also going to have equal capabilities. We don't want any kind of variation there. Each decision is going to be made in the hierarchical decision tree of the hierarchical generalized processor sharing policy is going to have a 50-50 probability. So looking back at this, each of these would only be 50%. And we're going to have 4 classes in existence. We're going to have system admins, we're going to have staff, we're going to have student, and we're going to have guests. We're assuming that we're applying this in the Citadel network, perhaps at the Daniel Library, for example. Alright, results and conclusions. We're going to make our conclusions based upon the sojourn time and throughput. Sojourn time, I don't know if I'm pronouncing that right, is the total amount of time that an object spends in a system before being transmitted, and throughput is a calculation of the units of information that a system can process in a given amount of time. We're going to be breaking that data down, giving a class comparison, which classes were best served, and by what margins were they better served than others. Now and we're going to be comparing the process sharing network versus the non-process sharing network. So basically we're going to run this twice. We're going to run it once where it is going to have this policy of CPU utilization exceeds 90%, and then it's going to start issuing unserved processes to neighbors, and once we're going to be running it without this policy. And we're going to compare those side by side. Alright. Future work. What do we need to consider next? Well, I did mention earlier that there were plenty of other things. For one thing, we do need to consider machines with different capabilities, because they are not a one-size-fits-all system, especially if we want to stick with Cord, which is an ad hoc kind of system. Anybody can join or leave at any time. We're also going to be considering using Gaussian processes as opposed to the earlier Markov modulated Poisson processes to model the randomness with which tasks appear and disappear. We also have to consider security issues, definitely, because not only are we exposing our processes to those machines which are being trusted to process them, we're also exposing our own processor to other machines that can basically request that we execute process for them. So there are definitely security concerns that need to be explored. We should explore other topology, network topologies. Perhaps we'd rather go with something a little less structured than something like Cord. And we also need to consider expanding outside of the existing network. If it works well inside and we can keep it secure, then we definitely are going to want to see if we can leverage the utilization of other machines potentially outside of the network. Willing machines, definitely. We don't want to create a botnet, but this is definitely something that is worth exploring. I'm going to have to wrap things up really quick here because the software I'm using to record this only lets me do up to 15 minutes, but I really hope that you enjoyed this and that you give it some thought and consideration, because I definitely enjoyed working on this. Thank you.